Hey guys, it's Miss Rainey. Today we're going to talk about the three simple gas laws, Boyle's law, Charles' law, and Gay-Lussac's law. Let's get started. So the first gas law we're going to talk about today is Boyle's law, named after Robert Boyle. He lived in the 1600s and was one of the first modern chemists. He talked about the relationship between pressure and volume. And he said that pressure and volume are inversely proportional, which means if one goes up, the other will go down. Inversely proportional. We also have a formula to solve for Boyle's law, which we're going to use in another minute. And it's also important to note that in Boyle's law, temperature is constant. So the only variables that are changing are pressure and volume. So, what will happen to the volume of a gas in an enclosed syringe if you put pressure on the plunger? Well, just like we said in class, if you put pressure on the plunger, the volume will decrease. All right, before we get into Boyle's law, I want to make sure and remind us about some pressure conversions. Standard pressure is 1 atmosphere, which is the same as 760 torr, which is the same as 760 millimeters mercury, since those two things are identical. And although your notes don't have this on there, we're going to add in 101.3 kPa. So if we were going to convert, we would take 825 torr, times sign in a line and put torr on the bottom, and ATM on the top. We'll use our conversion fractions that 1 atmosphere is equal to 760 torr. And then, handy dandy calculator says 825 times 1 divided by 760 is 1.0855, or 1.09 atmospheres. When you're converting pressures, you're going to use dimensional analysis. So if we had 0.5 atmospheres that we were going to try to convert into millimeters of mercury, we would put atmospheres on the bottom and millimeters mercury on the top, and say that 1 atmosphere is 760 millimeters mercury. And handy dandy calculator says 0.5 times 760 divided by 1 gives me 380, which has two significant figures, just like 0.50. And then, since a torr and a millimeter mercury are the exact same thing, 0.5 atmospheres is also 380 torr. So let's just keep these pressure conversions in our mind as we go forward here. All right, here's our first Boyle's law actual math problem. Have your calculators handy and let's get started. A sample of oxygen with a volume of 800 milliliters at a pressure of 1.0 atmospheres is to be compressed to a volume of 400 milliliters. What pressure is needed? So the first thing I'm going to do, which your notes has already done for you, is write down the information from the problem. 800 milliliters at a pressure of 1.00 atm is compressed to a volume of 400 milliliters at what is the new pressure? So here is my setup. Now, earlier we said Boyle's law looks like this. P1V1 equals P2V2. And so these are the initial pressure and volume and the final pressure and volume that we can just plug these numbers into. So our P1 is going to be the 1 atmosphere, and our P2 will be the question mark. Our V1 will be the 800 milliliters. Our V2 will be the 400 milliliters. And so then we're just going to plug it into that formula. 1.00 atmospheres times 800 milliliters equals question mark atmospheres. Remember, I always like to solve for the question mark, times 400 milliliters. And now, using my crazy mad algebra skills, I'm going to divide both sides by the 400 milliliters. So that on the right-hand side, the 400 milliliters cancels out. And on the left-hand side, just the milliliters canceled out. So I end up having 1.00 times 800 divided by 400 equals 2.00 atmospheres. Which kind of makes sense because the volume went down by half, so the pressure should go up the same amount. Pressure was doubled when volume is halved. All right, now I want you to look at this problem and see how different it is and how the same it is. 5 liters of nitrogen has a pressure of 825 torr. What will be the volume? That's where my question mark is. If the pressure is increased to 3 atmospheres. Well, that's kind of weird that they said the pressure is increased to 3 when it starts at 825, but then we realize that our units don't quite match up. We have torr and we have atmosphere. We need to convert one of those to the other so that both pressures are in the same units, which is why we learned about those pressure conversions. It really, truly doesn't matter which one you convert, just one of them to the other. So I'm going to convert atmospheres to torrs because I felt like I had more space to do that, but you can do the other way as well. And I get 2,280 torr. At this point, it becomes identical to the problem we just worked. P1, P1 V1 equals P2 V2, and plug it in. So that's 825 torr times 5 liters equals P2, that's 2,280 torr times question mark liters. I'm going to divide both sides by 2280 torr. So that the 2280 torr cancels on the right-hand side. And on the left, I am left with 825 times 5 divided by 2,280, which gives me 1.8092, or for 3 significant figures, 1.81 liters. And then we always want to double check and make sure that it makes sense. So notice that my pressure did go up from 825 to 2280, and so my volume should have responded by going down, and it did from 5 down to 1.81. So you always want to make sure you check that your answer actually makes sense with your problem. All right, so now we're going to skip that temperature conversion section of your notes since we've already done that and jump into the Charles law section of your notes. This one is named after Jacques Charles. He was a French chemist in the 1800s, I believe, and he talked about the relationship between temperature and volume. And he said that temperature and volume are directly related. So if one goes up, the other one goes up. Temperature and volume are directly related. And then we have a little formula to solve for it. Notice that in this one, pressure is constant, so we're only dealing with temperature and volume. So what will happen to the volume of a gas in an enclosed syringe if you heat the syringe? Well, those molecules are going to go faster and faster and faster and faster and faster, and then they are going to increase the volume of air. So the syringe is going to get bigger and bigger and bigger. There we go. All right, let's try Charles' law problem. A sample of helium has a volume of 300 milliliters at a pressure of 20 degrees C. What is the temperature? That's my question mark. If the gas expands to 600 milliliters. Now the first trick here with Charles' law is that we need to, hold on, let me get my and sign a little better. Never, ever, never use Celsius in a math problem, ever. We have to only ever use Kelvin. So I cannot use 20 degrees C. I have to add 273 to that, and make that 293 K. I cannot ever, ever, ever use degrees Celsius. I must use Kelvin. And so when I find my answer, it's going to come out in Kelvin. And then I'm going to solve it again and turn it back into Celsius when I'm done. Oh, and see what I just did. Let's fix that up. Okay, so here's how it works. V1 over T1 equals V2 over T2. Here's my volume 1. It's my first volume. Here's my temperature 1. Here's my volume 2. And here's my temperature 2. Plugging it in, I end up with 300 milliliters over 293 K equals 600 milliliters over question mark K. Has to be Kelvin, cannot be Celsius, must be Kelvin. At this point, we're going to cross multiply and divide by what's left. So that is 293 times 600 divided by 300 gives me 586 Kelvin, which would be fine for my final answer, except that the problem says how many degrees Celsius, which means minus 273 equals 313 degrees C. To check the reasonableness of that number, notice that volume goes up, so temperature should go up. So if one of them goes up, the other one should go up, and it did from 293 Kelvin to 586 Kelvin. Also, the temperature did double, but not the Celsius temperature. It was the Kelvin temperature that doubled from 293 to 586. The Celsius temperature won't double, and that's why you don't want to use Celsius, because you're going to get a wrong answer. So always change to Kelvin. Let's try another one. In fact, this one I think you could probably try on your own if you want to pause the video now and just see what you can do. All right, let's work it together. I've got 3.0 liters of helium at 25 degrees C is cooled to 5 degrees C. What is the volume of the helium at 5 degrees C when the pressure is constant? First step, always, is to change Celsius to Kelvin. You may not use Celsius in a math problem. You will get the wrong answer. Then I can see, look at my temperature, how it's gone down. So I'm going to predict that my volume should go down. I'll plug it into the formula that I have. And my V1 is 3 liters. And my T1 is 298 Kelvin. My V2 is question mark liters. My T2 is 278 Kelvin. I cross multiply and divide, and I end up with 3 times 278 divided by 298 equals 2.79865, or 2.80 liters. The significant figures are kind of weird here. Remember, when you add, subtract, you're looking at places past the decimal. So even though that's 5 degrees C, which looks like it would be one significant figure, when you add it to 273 for 0 places past the decimal, it actually turns into 3 significant figures. So we should have 3 significant figures in our answer. 2.80 is correct. All right, and our last law is Gay-Lussac, named after Joseph Louis Gay-Lussac. He lived in the late 1700s, early 1800s. He was a French chemist, and he actually discovered that water is 2 parts hydrogen and 1 part oxygen. Okay, but for our purposes, his law has to do with temperature and pressure. So he said that if temperature goes up, pressure will also go up, because temperature and pressure are directly proportional. And so we got a formula for that. He says that volume is constant, so we can completely ignore volume when we're working with Gay-Lussac's law. So what would happen to the pressure of a contained gas if its temperature is lowered? Well, if the temperature goes down, the molecules will move slower. They move slower, then there will be less collisions. So the pressure will decrease. All right, let's try a Gay-Lussac's law problem. A steel cylinder contains a sample of neon at a pressure of 760 torr. So that'll be my first number that I'm going to write down. And a temperature of 25 degrees C. What will be the pressure? There's my question mark. If the neon in the cylinder is heated to 400 degrees C, as you might have in a fire. Volume is constant, which means ignore volume. First thing we're going to do, always and forever, is change the Celsius to Kelvin. We cannot use Celsius in a math problem no matter what. So 25 plus 273 is 298 K, and 400 plus 273 is 673 K. So that's my first step. Then I'm going to identify, I've got a pressure 1, a pressure 2, a temperature 1, and a temperature 2. Notice my temperature is increasing, so my pressure should increase according to Gay-Lussac's law. Formula is P1 over T1 equals P2 over T2. And then I just plug it in. My pressure 1 is 760 torr. My temperature 1 is 298 K. My pressure 2 is question mark torr. My temperature 2 is 673 K. I'm going to cross multiply. That is, multiply the numbers that are across from each other and divide by what's left. 760 times 673 divided by 298 gives me 1716.376, and for 3 significant figures is 1720 torr. Notice here 1720 torr is a higher pressure. Since pressure is supposed to go up, that means we've done something right. Alright, finally our last Gay-Lussac's law problem. A cylinder of hydrogen at 25 degrees C has a pressure of 1.50 atmospheres. What temperature in degrees C is required to bring the pressure down to 0.5 atmospheres? First and foremost, always, we're going to change Celsius to Kelvin. We cannot use Celsius in a math problem ever. Then I'm going to notice that pressure is going down, which means temperature should also go down. Pressure and temperature are directly related. And then I'm going to plug it in. And so, plugging it in, I have 1.5 atmospheres over 298 K equals 0.5 atmospheres over question mark K. We're going to start with K. Cross multiply will be the numbers that are across from each other. Divide by what's left. 298 times 0.5 divided by 1.5 gives me 99.3 Kelvin, which would be great if I wanted Kelvin, but it specifically says what is the temperature in degrees Celsius, so I'm going to have to minus 273 from that and find out that that is negative 174 degrees Celsius. And there's my Gay-Lussac's law. I hope you guys had fun. We'll see you next time.